All right. So today we are going to be looking at parallel RC circuits and all the changes in equations and stuff that come with that. So last time we went through and we talked about the complex plane. So this is going through and converting between what we refer to as our rectangular coordinates. So we have A, which is our real value, plus JB. So J here is our term that we're going to be using for imaginary in this class. And then B here is the imaginary component. And we can go back and forth between it and the polar form. So that is the C angle plus or minus theta. We're going through and figuring that we can use sine, cosine to go from the polar form to the rectangular form. And we can go from the rectangular form to the polar form by using inverse tangent and Pythagorean's theorem. We then went through and talked about for a series RC circuit, how to go through and write out our value for Z here. So our impedance. So our real term is going to be the resistance term, the imaginary term being our capacitive term. So that minus J is rotating at 90 degrees. So if we were to go through and draw out that phasor, we'd have R over here. And down here to some value, we would have our XC value. And we can go through, again, the top equation there is technically the rectangular form. The bottom equation there gets us into the polar form of the equation. So both of those are the impedance, and we can go back and forth between them however we want to. Any questions from last time? Today we're going to talk about impedance and admittance of parallel RC circuits. We're going to talk about how do you do some of the analysis for these circuits. And then we're going to talk about how do you combine series and parallel RC circuits. So for the parallel and RC circuit, what this means is that when we go through and do everything, our equivalent resistor is, or the total resistance is parallel to the total capacitance or the equivalent capacitance value. So here we have a circuit where we have our resistor and capacitor. They are parallel to each other. So with this here, again, typically we are going to be seeing this in terms of an AC circuit. So we are still going to be able to go through and use XC for the capacitor. What is XC for a capacitor? No. What is it? No. What is X? What's the definition of XC?
1/2 pi frequency capacitance.
Yes. This is still going to be true. We're still going to be able to utilize this equation this way. Once we do that, right, that is the resistance essentially for right, the capacitor. Going through and then finding the impedance is a little bit more complicated in comparison to what we have for them in series. Because in series, we can just add the two together. What is the equation for resistors in parallel? Yep. So we would have to do that for these two as well. Because we have inverses involved, that is division, so very often you'll see this done in the polar form instead of doing it in the rectangular form. But it looks a little something like this once you go through and combine them together. So here we have Z, which again, Z is going to be used to represent the impedance. It's going to be equal to the resistance value. So here the angle is given because the voltage is in phase with the source. And then we have XC minus 90 degrees because it's going to be lagging that 90 degrees value for the capacitor divided by R minus JXC. If we're being honest, we very rarely will use the equation in this form. You can simplify it down a couple of different ways. The textbook does all the individual steps. I'm cool just jumping to the result. It's going to look something like this. So this is how we can get our impedance in the polar form. From the polar form, we can then go through and get that rectangular form. So here for the magnitude, it's going to be RXC divided by the two magnitudes squared and added together, then square rooted. And then the angle, and this is something that we need to be aware of, is this negative sign here. As somebody who drops it rather frequently, we do need to remember that this exists. It is negative inverse tangent of R over XC to go through and find the value. The reason the equation itself needs to be negative is resistance has to be a positive value, and our XC value also has to be positive. But again, because there's going to be some lagging, we need that negative angle value. Any questions so far on the parallel RC circuit? So with that, and in general with parallel RC circuits, it's not always going to be the best to go through and look at the inductance. Sometimes it's going to be beneficial to go through and look at the inverse values instead, because this might make our math a little bit simpler for going through and solving. Of the examples I've chosen, that's not going to be the case until the last one that we probably won't have time to finish, but we can at least see a little bit there where it is. So with what we're going to talk about on this slide, so the conductance and stuff, these are all things that you can use. You do not explicitly need to go through and utilize these values. So it's a choice to go through and utilize. So for conductance, we did actually talk about this very, very, very briefly at the beginning of the semester. It's the inverse of the resistance. So here we have its equation. We have G is equal to the inverse of the resistance value, so just 1 over R with 0 degrees. So its value will just be G 0 degrees. So just inverse that value. Surprise, they're all just inverse values of something else. So we have here, we have our BC. We will have a BL as well. This is the inverse of our, or the reciprocal of the capacitive reactance. So with this here, when we have division for something in polar, for the angle portion, if it's 1 over that, it just flips the sign. Because again, what we would go through and do for this is we would have, what this one would end up working out would be 0 degrees minus 90 degrees to get us the positive degrees that we have here for BC. Which means that if we were to go through and look at it in rectangular form, it's plus JBC. So the equation, right, it's inversed. It is inversed in angle as well. It's instead of negative 90, it ends up being positive 90. And last but not least, we have the admittance. That's going to be Ry. It is the reciprocal of G. Or sorry, not G, Z. So 1 over Z. So for the Z, it can be positive or negative theta. When we go through and flip that over into Y, it becomes negative positive for the theta value. For the same reasons, it flips for any other polar coordinates. Like I said, these are technically optional for going through and looking at our circuits. It's all going to depend on what you are more comfortable with doing. In some examples, it might be just as easy to go through and just use the equations we talked about on the previous slide, rather than going through, finding all these, and then flipping it back over. Because at the end of the day, very often we still are going to be going through and looking for the impedance value. So all of these here are just to help you go through and do the math. Still, very often at the end, we want to go through and flip over the admittance to get that impedance value. That is the more important value of the two of them. With all of these here, they share the same units, which is going to be 1 over ohm, or the Siemens unit. It's given with the S. So all of these share the same units, just like we have for resistance, reactance, and impedance. Those are all in ohms. All of these are in inverse ohms. Any questions before we give our first example a go?
Assuming you'll explain what the purpose of Siemens are.
They're just units. 1 over ohms. That's it. Yep. They're not useful. These are typically, again, mathematical helps.
Okay.
For solving, they're not. They are things you can technically measure, but they are not the important measurement that you would want for a capacitor or a resistor. Oh, sorry, that's on the next slide. So this one here talks about when you might want to go through and do them. So with parallel, like I said, it might be easier to go through and do this, and this just tells you what you would replace which with which. So it, right, and again, the key thing we want to look at here is it can. It won't always be, but it can be easier to go through and use these. So what you'll do is you'll look at the question, establish what you think the best approach is going to be, and then based off of that, either go through and use right, R, X, C, Z, or you can go through, do G, B, C, Y, and then go through and solve. So this can be what the circuit looks like instead. So instead of R, X, C, we can have G, B, C. And then same relationship with the admittance with its variables as impedance with its. But now the vector points up instead of pointing downward. So it is rotated 90 degrees or flipped about the positive real axis. Or sorry, mirrored about the positive real axis. So 100% optional to go through and use. Do not have to use this if you don't want to. So if you look at some of the examples in this part of the textbook, sometimes they'll use these, sometimes you won't. So I do recommend going through and looking at those to see kind of when the textbook is using them versus not. Now let us do an example. So I want you to look at this circuit here. And at the end of the day, we are looking for the impedance magnitude and the phase angle theta. So I want you to look at this circuit here and decide, is it going to be easier to use the RXC, or do we want to use, sorry, I can't ever remember the other letters, GBC. Which ones do we want to go through and utilize here to solve?
That circuit first. Doesn't mean a lot of math either way.
This is the short question for the day. This one is not bad.
Yeah.
So before you guys commit, what's something you might want to go through and do first?
Determine the total capacitance and the total resistance.
Yeah, you can go through and do that first. There's nothing wrong with simplifying a little first. So for RT, what are all of my resistors in?
Series.
They are also, yes, they're in series and in ohms, so I don't need to worry about converting. I can just go through and add all of them together. So I'll have 470 plus 330 plus 680, right, 1,480 ohms. What are the capacitors?
Parallel.
They're in parallel. They're also both in microfarads. So we are able to go through and keep it that way. If I'm going to solve for XC, I need to have my value in farads. So we can decide to convert them both and then do the total value, or we can do the total, then convert. Sure, you can do it that way. So because they're in series, what do we do to get the total value?
They're parallel.
Yeah, sorry, parallel. Yep. We what?
You would add them together.
Yep, so we'll have 0.1 microfarads plus 0.22 microfarads, 0.32 microfarads, 0.32 times 10 to the negative 6 farads. So if I wanted to, I could go through, I could redraw this circuit. I don't know if it helps us do this. It does confirm that our total resistance and our total capacitance is in parallel. So this means that we can go through and utilize parallel equations. in which already so far in the past 20 minutes of class, we have talked about really 4 unique equations. So we have to decide how we want to go through and solve this. At the end of the day, I want my z value and its corresponding theta value. With doing that, do I need to use these equations here? Why not?
Because it's extra math to get to the same point.
Okay, so what do you want to use instead?
The
So we can, for this one if we want to, we can just start with this impedance equation here. So we can find XC, we're gonna need that anyway to find BC. And we already have R, so we can just directly use this one here. This is perfectly valid to go through and start at this location. This is still technically considered a relatively simple parallel RC circuit. So we can go through and we can start at this point. If you go through, and let's say you want to go through and you find the admittance, you can do it that way. You'll probably want to do it in polar before you go through and try to convert it into the Z value. So I'm going to find X C 1 over 2 pi. What do I need to do to my frequency here? Oh,
it's start disconnect back on.
what do I need to do to the frequency?
Times it by 10 to the third. Okay.
Or just write 2000. I'm just not going to put my units in here. Again, when I use this equation, my frequency needs to be in hertz. My capacitance needs to be in farads in order for this to go through and pop out in ohms. We'll have my 0.32 times 10 to the negative 6. Which I got 248.6796 ohms. You guys okay?
Yeah.
Disagreeing with signs?
One wants to do it one way and the other wants to do it the other way.
That's fine, because they don't get to work on the exam together, so they can turn it in different ways. Questions up until this point? So if I'm going to go through and do this, then I can go through and just use Z is equal to R XC over the squares added together square rooted. So I'm going to drop my units for going through and doing this to get my values. So I'll have 1,480 times 248.6796. If I'm being honest with this one here for the XC, I'm only carrying more sig figs than I want. But that's because I have a 9 there. I'd rather carry too many rather than too few. Square root of those same values squared. Taking those and plugging them in, I got 245.242. That's going to pop out in ohms. When I do my inverse tangent with this method here, I need to make sure that I have that negative sign with it. So I'm going to have negative inverse tangent R over XC. So when I took this and did it, I got negative 80.4619 degrees. Again, when I'm doing this, if I'm have my calculator in degrees, I need to indicate that my angle is in degrees. If I have it in radians, and it would need to indicate either I don't put the symbol there or I put rad for radians.
It's, there's the connection issue. It'll turn back on, right?
Does it change how you do it?
I guess IT will be coming back for a third time. It's just going to be off. It's just going to be that way for the rest of the class. Sorry about that. But writing it out, I will have 245 ohms, or sorry, 245 negative 80.5 degrees ohms. So if you look at the textbook for this part here, sometimes it puts the ohms inside, sometimes it puts it outside. As long as it's somewhere, I will be happy with it. So make sure you have it. You could have also done it as 245 ohms, angle 80.5 degrees. Any questions on 43? So again, you can go through, do it to solve for y. Where you would start splitting off is after solving for xc would probably be the safest place to split that off. But again, for this particular question, it's not necessary. If it starts flashing, let me know and I'll unplug it. Oops. Oh, forgot animations on this one. So here we have some of the things we can go through and do with these findings. So this does give us a new version if we are using right, the inverse values. We have a slight variation in Ohm's law here. So all of these are bolded because these are you would need to go through and include the angles for these. So we must include the angle. So with it here, what? Yeah, you would have, so you'd have the Y value with its angle to go through and plug it in here. Stuff ends up getting flipped over a
So-
little bit.
In the previous slide, we solved for the z value, correct?
Yes,
Okay, so we would need the inverse of that z value to figure out the y.
we could use, yeah, you can take Z, inverse it to Y, or you can just use Z directly.
Okay.
Both are valid.
Situation times. So I.
Yeah.
Oh, you times it by.
Mm-hmm.
Okay, okay.
Yeah,
Sorry, the.
right, because it's V equals IR.
Yeah,
Or when you have the capacitive circuit, it's IZ.
okay.
Z is or Y is the inverse of Z, so the
That's
equation.
what you're dividing by y.
Mhm.
Okay.
Yeah. So you have to include the angle because there will be some angle difference here. It's gonna be, we're part of the reason we're going through and we're not just looking at XC and we're going through and putting this into impedance is we'll have impedance for an RL circuit as well, and then for the RLC circuit as well. So it's going to go through and it's going to have a bunch of different things that we would need to consider. So we're just practicing the skills now to apply them in more depth moving forward. So for the voltage, right, because they are in parallel, they will all have the same voltage across them. Right? Kirchhoff's voltage law still is going to apply. Yeah, it still applies. Just sometimes it's a little more complicated to apply. So typically for the parallel RC circuit, we typically focus on current more so than voltage. So that is why you'll still see Ohm's law get brought up here. That is to help us find the current values through that particular branch. So what is the current being applied to the capacitor to charge it? What is the current that is flowing through the resistor, and so on. So with that, the total current, again, this is after you've gone through to combine into a single resistor and a single capacitor. We're going through and expressing the current as the sum of the two of them, because those are the only two branches that we will have. And that means that we can go through and we can again describe our current in polar form by using this equation here. So we have the resistant or the current through the resistor squared plus the the current to the capacitor squared, add them together, square root it. That will get us the magnitude of the total current value. To find the angle, inverse tangent, IC. I think it's supposed to be IR. Let me double check that really quick here. Yeah, sorry, this should be IR. Whoop. Yeah, sorry, that should be IR, not RC. So the current through the resistor. And this is a positive angle, unlike with the impedance. So this phase angle here also represents the phase angle between the current and the applied voltage. So if we needed that, that information would also be there. So if you go through and look at the textbook, it's going to have a couple more phasor diagrams if you want to go through and look at this. Questions about current in a parallel RC circuit so far? So that stuff's cool. That's kind of what you're going to be able to do with it. In reality, you are not always just going to have series or parallel. You can have combinations for both. So with these, depending on where you go through and look at, it's going to kind of determine how you might want to go through and approach that individual circuit. This textbook's going to look at a couple of different things for us to go through and do, but we're going to kind of section off our current into parts. And so with those parts, how as you get more comfortable, you might be able to do more of those parts at the same thank you, at the same time. But for now, we're going to kind of keep it a little bit on the simpler side for that. So we can convert between parallel and series. We can also go through and combine series and parallel. With going through and doing this, there are some steps that we'd have to go through and do. if we wanted to convert from parallel to series, it is more complicated than just going through and using Ohm's law, like what we did with a voltage and a current source. So for them to be considered equivalent, they both have to have the same impedance at the terminals. So the Z values at the have to be the same for both. That is for both the magnitude and the angle value. So that is going through and doing that. Again, when we do this, depending on the circuit that we have, might determine which way we want to go through and do. You might want to take parallel and convert it to series, or take series and convert it to parallel, because this will allow us to go through and sum those together. This is the textbook steps for going from parallel to series. If you look at most of the examples in this particular textbook, it's going to have the parallel portion of it as far away from the source as possible. So typically we'll want to start away from the source and then move towards the source when it comes to simplifying. Similar to what we did with our resistor circuits kind of at the beginning of class, right? We started a little bit further away and got closer. Kind of that same general idea here. So the first thing you'll want to go through and is determine the impedance and phase angle of the parallel circuit. So this can be done in a couple different ways. Again, it's going to depend on your exact circuit, on if you're going to want to use R, XC, or if you want to use G, BC. Then find Y, then convert that into Z. We'll want Z because when we go through and look at the series case, Z is all we've got. We do not have a Y equivalent for a series resistor. It has to be the impedance. So you'll use the values of Z and theta to construct what is referred to as the impedance triangle, which is what we have here. So it's just, you have Z, we can go through and find the real and imaginary components. So using sine and cosine, that is going to get us, basically it's saying convert it into the rectangular form. So this step here is convert to rectangular. The reason we'll want it to be rectangular when we get to our parallel to series is if we have two series, we would be able to then go through and add them together. Again, typically when we're adding and subtracting, the rectangular form is a little bit nicer to go through and use versus when we are doing multiplication and division, we might want to go through and use that polar form. So depending on which one we have, will determine which set of data we want to go through and use. Numerically, again, they are the same thing, just represented different to make the math for ourselves as easy as possible. Any questions so far? So I realized I probably should have moved this one. I forgot to. But this is 45 here. So this is before we go through and worry about converting. So for this circuit, find all currents and voltages in the polar form. So I want you to go through and discuss with your neighbors how we might get information to find the current values. Oops, sorry, that's my bad. Trying to see if I could send that to the other one.
So we find the occurrence by putting in system values. No, we should be able to figure out an occurrence. Right.
Right, so what might we want to go through to do to find the current values?
E value,
Why would I want to find the Z value?
I total.
How?
E equals height. E.
Or we could just start it with, right, I is equal to V over Z.
Yeah,
Or if we wanted to, because this is parallel, we could also do VY. Both in this case happen to be equally valid to go through and do because we are explicitly given XC. It's not any extra effort to go through and find BC. So both methods work out. Again, it doesn't matter which one you go through and do. As long as once you do it, you are committed to that method.
does 10, 0 degrees, 10 volts, 0 degrees have anything?
That is telling us that it is starting at sign. So that is a 10 volt sine, whatever, frequent omega t plus 0 in that case.
Okay.
So it is a sine wave for it, but we do need it because when we're using Ohm's law for Z and Y, technically we should be going through and utilizing the angles. So that's why the angle is given here. So we'll worry about Z or Y here in a second. What do I know about the voltages across my different components?
They're the same voltage drop
Why?
because they're in parallel.
So VS equals VC equals VR. So 10, 0 degrees. When I go through and I want to look at taking my values here. Sorry, they're not all 0 degrees. Let's take that back. Right, we have, oh, sorry, no, I was right. I'm getting a little ahead of myself. So with this here, right, they all have the same voltage. So they all need to share the same values. When we go through to look at the Z value, right, is this gonna give us the Z, the current through each individual component or the total current?
Total.
The total. So this is technically IT here. When I go through to look at, so IT is going to be equal to, let's just say hypothetically, we're going to do it with VZ. We can go back and change it in a second here. Let's say we're doing VZ. For IC, I would use V over what? Mm-hmm. And then for the resistance, right, V over R. So if I'm going to use Z, these are the equations I'm going to need to go through and use. If I'm using Y, it's going to be BC in VG. Again, technically here they are all going through and doing it fine. Does not matter which one we use, as long as we are being consistent with it. Questions before we start talking about XC, BC, R, and G in a little bit more detail here. So let's say we're looking at it for Z. Again, we can talk about Y here in a second. Right, this is R minus JXC. That is its definition. So when I go through and I utilize Ohm's law for these, if I'm using R, what should the angle, right? If I'm using R, it's going to be 68 ohms. What angle would I use for R? I don't want to put,
No.
this is just an angle. It is going to be 0. There's no lag for the voltage across the resistor. It's just the same. But there is for the capacitor.
Why this?
So for XC,
You need
it's going to, yes, it is going to be negative 90. We get the negative 90 from minus J. Right, that is pointing down in our whatever the complex plane, it's pointing down. That tells us it's negative 90 degrees. So those would be if we're using R and XC. What if instead I'm using G? Yeah,
It'd still be 0.
the angle's still going to be 0, but is it 68?
Why don't get 68 to the negative third?
Yeah, so whatever method you like to represent that. So 1 over 68, 68 to the minus 1, put in decimal points, whatever, it's fine. I personally like this version, but if you want to use the negative 1, again, perfectly fine. Decimal place, perfectly fine. It's at 0 degrees. What about for BG? Or sorry, BC, not BG.
Inverse of 90 with angle of. I almost think it's easier to visualize with radians because pi over 2 and
This textbook uses degrees. Some textbooks use radians. Some textbooks, in a really unfun way, do combination ones.
I think it's easier to imagine degrees. That's just.
You are welcome if you do it in radians, somehow just, again, don't put the degree symbol or put rad. I don't care.
think about the inverse of pi over 2 is 2 over pi.
The opposite of 90 is 270.
All right.
If you remember.
So- With that, questions? Yes.
So conductance unit is just 1 over ohm.
Mm-hmm.
Resistance is 1 over ohm.
Yep.
So they only remain in the first and fourth quadrant, right? Do they ever go into the second and third?
Not for capacitors.
Okay.
We'll be in those quadrants next week.
The circuit where your capacitors out of phase and in those.
All right. So we have everything we need technically to go through and do either Z or do Y. Right? We've done everything. We've done all the pre-work to figure it out. If I'm going to use Z, right, I would go through, I would have RXC over the squares added. And then for the angle, I would have the inverse tangent of R over XC. Right, this is the equations that were explicitly given to us for this. If we go through, I didn't show them in class where we just said that it's the inverse of it, but technically we have equations for Y as well. And we just flip it all
Y would
over.
Be the magnitude of top and the multiplication on the bottom, right?
Mm-hmm. And then for the angle, it's just the positive R over XC. So you get to decide which one you want to go through and do here. You should give us the same results regardless. Or -1. Questions? Did I flip my angle?
Yeah.
Okay, sorry.
RC. Does it mean equal?
It's inverse, so
Oh,
Yeah.
gotcha. The B
Well-
XC.
Excellent. Sorry. Why?
Oh. Oh, yeah, sorry. Just keep those where they are, fix those. So yeah, sorry, it's XC. So no, for Z it is R over XC for parallel.
Oh, for
We have parallel in this case. Series, it's flipped over. Here, so R over XC. And then
XC.
since it's inversed for this one, I'm just trying to double check. Sorry, sorry. Let's redo Y. For Y, we can use, instead of using XC and R, we should use G and BG
Okay.
inside of it. Because those are the correct ones. So we'll have B, C over G. And then, sorry, I don't think I wrote down the equation for Y. You would think I would write things down. Sorry, Y is just equal to the square root of G squared plus BC squared.
Looks like a series.
So it
Yes.
doesn't get the
Because it's inversed, it looks more like series.
okay.
So this,
Makes sense when you write out.
yes. So now that we've fixed the equations, either of these methods works out. So we can find Y and use its theta value, or we can go through and we can use Z and use its theta value. Again, we have all the information we need for both. So, out of curiosity, which one do you guys want to go through and use? Just in general. How many of you want to use Z? All right, we are using Z. All right, so to go through and find Z, I'm going to assume you can plug in the numbers. R is given, XC is given. So we will have 54.255 with an angle of negative 37.073 degrees. That's just going through, plugging everything in. I now can take this and plug it in for IT. So IT is going to be equal to my voltage, so my 10, 0 degrees over 54.255 negative 37.073 degrees. We didn't really spend time doing this yesterday, so let's, or not Tuesday. So let's just talk about it. For the magnitudes, we just divide, so we'll take 10 divided by the 54.255. That's going to get us the magnitude part. For the angle, I'm going to take my 0 degrees. I'm going to subtract the 37 or the negative 37.073. So I have minus minus, so it becomes a plus. So assuming I did this correctly, I got 0.184, 3, whatever the rest was, amps at an angle of 37.1 degrees. So this here is IT. That is my source value. We have done 2/3 of this question. Now, well, we did a lot of meandering around first. But now we're ready to just solve the last ones. Questions up until this point, though. All right, so to find IC, I'm going to have 10 over 0 degrees. I'm going to use the XC equation that we came up with above, so 90 with an angle of negative 90 degrees. So this should get us right 0.111 repeating amps at 90 degrees. And then for IR, again, I'm going to use that same voltage value. This time I'm going to have 68 at 0 degrees. So that is going to get me 0.147 amps, 0 degrees. Again, assuming I did math right. 1 second before I forget the exact thing I wanted to do. Yes.
So I'm a little lost in how you divide an angle by another angle.
So you do the magnitude of the two magnitudes, you do normal.
Okay.
And then for the angle, it's top angle minus bottom angle.
Okay. Cool. That's all I needed to know.
Yeah. Any questions about 45? So for this here, again, sorry, I put that in the wrong spot. We just want to kind of talk about series parallel a little bit more. So the impedance of series components is best expressed in rectangular. So that is going to be the A plus JB. And the impedance of parallel is best in polar. Again, C, something to do with an angle value. So when we look at our circuits, again, this is kind of what I alluded to earlier. I want to look at the two different parts separately. So here we have a circuit where we have a resistor and capacitor in series and a second set, but those are going to be in parallel. So with this here, when we're going through and doing this, we have two Z values. And this is something that we should work on keeping track of. So this textbook, it's going to have the shaded areas over it. Some textbooks put a little box around it and label it. The box part's probably a little bit easier to go through and execute. So here we just have a box around R1, C1, and we're calling it Z1. Yes.
What's Z2 in? Or in the series form, could you, or what would you combine the Z's?
Getting ahead, but yes. Yeah, so the idea is typically you'll convert your parallel into a Z value, and then you can just add them all in series together. So, but when you do that, typically while you go through and do the math, your Z will pop out in polar for the parallel part. So you'll do that one extra step of converting it into rectangular, then go through and add them. They need to be in the same format. You can, but adding polar tends to be a tiny bit harder to go through do. Yes.
So, is it possible for us to have our Z's parallel? Where we would technically have like, let's say there was a mirrored section of Z2 that was above it. So then how would we work at adding the parallel Z's together?
How do you add parallel resistors together? That's what we were going to do in the example. Yeah.
Oh.
Yeah.
You have the answer. Let's go.
That's fine. Believe me, we got a lot of work. We're not gonna get there, and that's fine. We'll practice just blocking it out. But yeah, you can if they're in parallel. Here they are in parallel. You just would add them like resistors in parallel.
Okay.
So typically first we'll want to express the impedance of the series part of the circuit in rectangular, parallel part in polar, go through and combine them. The reason we'll want to keep our parallel parts in polar is when we go through and let's say we're doing the right circuit here where we have the two that are in parallel. To find ZT, I'd have 1 over Z1 plus 1 over Z2 inversed. So with this here, by having it in polar, it's a little bit easier to go through and do the math. That way we don't have to deal with having two terms with two terms with J and things like that that need to get multiplied. So if it's in polar, technically it's a little bit easier. You could also, when they are in parallel, go through and utilize Y. You're welcome to still do that. That is still valid. It's just when we go through to add the series and the parallel together, it has to be Z. Cannot add Z's and Y's.
You have to pick one or the other?
Series cannot be in Y.
Oh, series cannot be in what I thought.
So
Good.
you have to have Z. Impedance is the way to go.
I was compared after.
I mean, you shouldn't be converting your series into inverse.
Well, no, but I mean, if
Yeah.
you have your Y's, you can, that's an easier.
Yeah, you can do all your Y stuff together and then convert it into one. But typically what you'll see in any introductory textbook is you've got one parallel, one series. Maybe if you're feeling saucy, two parallels together, but you're never going to do a series, parallel, series, parallel, series, parallel. That's just too much math for the sake of doing that. So yeah, these are just kind of the general steps for what you're doing. Yes.
So in the
Mm-hmm.
R2 and C2. Those are series, right?
For the one on the left or the one on the right?
What?
For R2 and C2 are in parallel. Because we could draw the line like that to connect it. Then you would call that one Z3. So you would do Z2 and Z3 separate, then combine them, and then. So kind of similar to what it's the same way we treated resistors. It's just we have to do some math to get those values first.
If we're being asked for currents in different sections, could we just create an equivalent circuit for sections of Z's or Y's? And like put the different parts together and just give the current for this part of the circuit?
Like this part being this Z section.
Unless if we're asked for specific capacitor resistor currents.
Yes, that is fine. So the example that we're gonna talk about here has you going through and doing that, but I'm not gonna make you go through and do this whole thing. So, we'll talk about this in a second, but right, in general, you're gonna probably have in this class, you will probably have parallel to deal with first. Convert that into a Z value in whatever method you're comfortable with. And that will probably pop out in polar. Convert it to rectangular, add it to the series. Did that answer your? Get a hand up. Or no? Oh, were you strapped? I thought your hand was going up. Yep. All right, so let's talk about this one. We are by no way, shape, or form going to finish this whole thing. It's a lot. So this one here, right, determine the voltages in polar form across each element, draw the phasor diagram. So first, let's discuss phasor diagram. If you have to draw a phasor diagram on the exam, as long as it's pointing roughly in the correct direction, roughly correct magnitudes, that's fine. So I'm not gonna sit here with a ruler and like slapped on my screen and be like, oh, this is off at an angle. No, don't have time for that. So if it's something that explicitly should be larger, that vector should be longer. I am not going to have us go through and do something with this here for the next exam that has you combine it all together and then backwards finding like the voltage or the current. I'm going to get to the point where we find Z total, and that's enough. I will be content with that for this type of question. So we're just going to go through, and in reality, instead of doing this, what is ZT? So I just want to look at this here. And I kind of just want to discuss the circuit diagram and looking at how we want to block this out. Because there's a couple different methods to go through and block this out. So let's talk about what we have going on to just start with. So for C1, is it in series or parallel with any other circuit components?
Series with the resistor.
Yeah, so it's kind of by itself. So what we're going to go through and do is we're just going to put it in its own little individual box. We can name the box later if we want to. We will, but we'll hold off on it. What about if I go through and look at it, C2 and R1? What are, they're in series. Are they, and it's just those two. We're going to put them also in their own little box. Weird shaped box, but I don't want to cut off the numbers. So for C3, is it in series with anything?
No. It's
No.
in parallel with the R2 and R3.
So it's in parallel with R2 and R3. Yes. So we have a choice. Probably the safest choice is to put C3 in one box and then put the resistors in a different box. So this is probably the safest way, especially because this is new, to go through and approach this. So what I'm going to do is I'm going to redraw my circuit. This redrawing part's optional. Blocking it out, technically optional, but I think it's really beneficial, especially if you're going to call stuff Z1, 2, 3, or ZABC, whatever notation you're going to go through and do. So I'm going to redraw this here. I'm not going to move my capacitor. I'm going to just do this. I will relabel them here in a second. We're going through and doing this. So I have C1, C2, C3, R1, R2, R3. Okay, so this is the same circuit, just drawn a little more spaced out. So again, I can go through, I can look at these, and with this, at the end of the day, everything is going to be in series with C1. So I need to deal with all the parallel stuff before I can go through and deal with that one. So I'm going to ignore it for now. I have to focus on all the stuff in parallel. So we're just going to ignore it for now. So for C1, R1, I need to deal with the two of these together. What do we want to call this? Okay. I'm going to deal with C3 by itself. So if I want, guessing based off of, if I'm going to go with Z1, probably want to call this one Z2. And that means that for the one on the right over here, Z3. And if I just felt like circling a bunch of different stuff, I can call this one Z4. It doesn't matter. So I have all these things and they're all labeled. So that means that when I go through to find ZT, I'm able to go through and do that. Again, Z is a measurement of resistance. So if I wanted to go through right now and find ZT, it would be Z4 plus 1 over Z1 plus 1 over Z2 plus 1 over Z3. Inversed. Again, impedance is a measurement of resistance. Has the same equations as resistors in series and in parallel. I am able to go through and do this, or I can have Z4 plus, at the end of the day, I still need to flip it over, Y1 plus Y2 plus Y3. Inverse. I would need to inverse it because I can't add Y and Z together. I have to add Z's. Questions? You don't like Y, you can keep it in Z. Yes.
So for Z2, 3, and 4, they don't have the other respective parts, so
It works because they're in series. If we had it in parallel, so if R2 and 3 were in parallel together, you'd have to include it with C3 as well, because then you get stuck with 0 the way the equation works, but because they're in series, it checks out, because if we have a sea of zeros,
Yeah.
it doesn't do anything.
Well, the thing is, how would you set their equation?
Well,
You would write it
is it impedance equal to resistance? If that's all it is in the series?
Mhm.
RZ would be.
So- Z3 is just gonna be R2 plus R3. It's just adding those two together. That's all we have. There's no capacitor, there's no imaginary component.
So if there were, but like, what's? It's just,
We figure out the X value.
okay, it's the. It's
Or sorry,
essentially-
X2.
It's essentially like Z is just essentially either, XCT or RT in those specific points.
Yes, and in that specific branch, what is RT and what is XCT?
So Z2 would just be negative JXE. That's three.
You have the packet in front of you, but yes,
To the right.
that's not my problem.
No, it's not.
But yes, so these would be the equations. I will record a video of me getting to ZT tonight. And I will post it and just show you guys kind of the general process for it. But yeah, it's going through figuring out what should your equation be. So yeah, you should be using totals and things like that. But yeah. Any questions on 51 so far? I will see you guys on Tuesday.
That's what you want in the script. So adding the inverse version of the square